Hello, everyone. I'm Shuinai Zhang from Purple Mountain Observatory in China. So here is the outline in a clockwise direction. Don't worry, most of them just in one page. Generally, we talk about the history of charge change, the software required in the exercise material, and the high-resolution spectrum. We take a bit more effort on the diagnostics and show one promising case and explore its results. At last, we take a glance into the future observations and see the benefits with the charge change process taken into account. However, I see you know why it's worthy first. So begin with the benefit. Now, when you talk about the CIE and EI photoionization, you're talking about the state of one plasma. But for the charge change, it tells about the interaction between multi-phase gas. Let's see what kind of immediate benefits can be obtained from observations and how spatial information it may bring. If the charge change occurs, but it's not considered during the data analysis, for sure you will get the biased temperature and the matter abundances. The interaction area is normally unknown. And the velocity of diffuse hot gas is very difficult to measure. That's the interaction speed is hardly observed. And you are mistaken the charge change emission as part of the thermal gas. Nevertheless, if you take the charge change into account, these difficulties can be overcome. The temperature and the abundances can be rectified. And since the charge change only occurs at the skin of the cold gas, you will get the interface area. You can obtain the interaction speed by the line ratios. It's quite a unique way, right? At last, you can see the distributions of the thermal gas, the charge change emission, the temperature, metal, and the velocity. And I will show the case at the end of the talk. The charge change is not new to us. We can recount its early studies back to 19 years ago. Then in 1990s, the X-ray emission from the dark side of the moon and from the cold comet suggested the charge change process due to the solar wind charge change. Thanks to Dennis, who have told these stories in detail and show many beautiful images at the first day. Later on, charge changes started in different fields outside of the solar system, outside of the Milky Way, and outside the galaxies, because the multi-phase gas interaction is indeed everywhere. The hints of charge change is accumulating, and the scenario explains some observations quite well. However, due to the data issues or other contaminations, yet we are unable to confirm the scenario exclusively for the fields under this dashed line. Here, Randall made the AtomDB charge change model that includes a complete set of ions and radiative transitions, and it can be used to fit the spectrum in combination with other thermal models. We have also applied it to the star formation galaxies, since it's still version 0.4. And currently, the ACX version 2 only works in the Python frame. So I made some exercise materials in case you want to see how it works. Jupyter Notebook is needed to open it, and Python 3 is required for using PyIdenDB. If you have installed XSpec, then you should have PyXspec, and you need to install PyIdenDB and ACX2 that can be found on the IdenDB website and also the detailed documentations. ACX2 uses the energy-dependent cross-sections, which means we can constrain the interaction velocity now. The charge change model in Specs uses the CM database, and based on our naive comparison, the difference is not obvious in the soft X-ray band. Next, we talk about the high-resolution spectra. Generally, high-resolution spectrum should have energy resolution less than 10 eV, which is important for separating some diagnostic lines. In comparison, that of the CCD-like detectors is about 100 eV. The high-resolution instruments, including HTG and LTG on board Chandra, RGS on board X and Newton, and SXS on board Hitomi. There are tens of strong lines in their spectrum. How to recognize them? Here is an example of the RGS data showing some important lines from 10 to 6 Kelvin plasma. Roughly, we have Lyman series lines from hydrogen-like ions. You can see Lyman alpha, beta, delta, gamma lines from carbon 6, nitrogen 7, oxygen 8, neon 10, etc. And then lines from the helium-like ions, they have KR triplet lines, R lines, combination lines, and forbidden lines. You may separate them in a high-resolution spectrum, and you also see K-beta line, K-gamma line, and so on. And then iron lines mostly from the air shell transitions. Of course, in other situations, you may see more lines, but it's beyond the scope of this talk. Now that we have the high-resolution spectrum, how to seek the charge change? One feature we preferred is the oxygen 7 helium alpha triplet. Oxygen is abundant, and the RGS has a good effective area around 20 angstrom. This is a simplified Gaussian diagram showing the energy levels of oxygen 7. The helium alpha triplet lines are resonance line, combination line, and forbidden line. In a CIE plasma, levels 7 to 1 is a broad road that most electrons go through. It produces stronger R line, but in the charge change process, more electrons are cascading down through level 2 to 5 and produce stronger forbidden line. And you can easily tell which line is stronger in a high resolution spectrum. For example, in the starburst galaxy M82, you can see the stronger forbidden line than the resonance line here. And we do see the severe interaction between the hot and the cold gas in super winds. A nest of the charge change process. The SX model fits the entire spectrum quite well, which produces stronger forbidden lines of the oxygen 7, neon 9, and magnesium 11. A quarter of a diffuse emission is from charge change, and the interaction surface area is about 1 order of magnitude larger than the geometric area. So the oxygen 7 helium alpha is very useful, but I have to say it's not enough. Oxygen 7 R and F lines may come from different ions. Here, the solid curve is for the R line and the dashed curve is for the F line. Both of the oxygen 7 plus and the oxygen 5 plus ions produces stronger forbidden line than the resonance line, which means either in a recombination process or in an ionization process, there are chances to have stronger forbidden line, not just in the charge change. More than that, due to the resonance scattering, the R line may be reduced significantly and makes the forbidden line appear stronger. As a result, to fully prove the charge change, more specific features are required. Fortunately, there are some. In most processes, the fluxes of the higher order lines of hydrogen-like or helium-like ions change monotonously. For example, in the CIE state, the ratio between the Lyman beta to Lyman alpha is about 1/10. Similar for Lyman gamma to Lyman beta, etc. In the recombination state, it's about 1/3. But for the charge change, it depends. Now, when the ion and the neutron atom come close enough, the potential barrier disappears suddenly, and the electron just goes into its favorable energy levels. As a consequence, you will see stronger Lyman delta line than the Lyman gamma line, or stronger K gamma line than the K beta line. That's the specific features of the charge change. You may try it in the iPi notebook inside the XIS material. However, these features are weak lines. Till now, they are not identified in the observations with enough statistical confidence. I discussed with Randall, we probably should find a more promising case for this workshop. Then we can convince you that the charge change is not just one hypothesis, one of many possible scenarios to explain the observations. It can be the scenario really happening outside our solar system. So we found one. In the center of the galaxy, you see the outflow, just like in M82, right? Where the H-alpha emission is around the X-ray emission. You can also see the CO share of the outflow, a good place for the charge change. Some of you may have recognized this galaxy. It's NGC 253. So let's go to the spectrum directly. They are from Bohr's paper. The outflow region is divided into 5 parts. Carefully, we see easily the stronger forbidden lines from the helium-like oxygen 7 and neon 9, right? And we see some interesting features, likely nitrogen 7 Lyman delta line and oxygen 8 Lyman delta line. Keep in mind, no strong lines are supposed to be there if not for the charge change. The paper listed 2 possibilities. First, could it be outflow? This shift in wavelengths would suggest a radial velocity of about 6,000 kilometers per second, not likely at all. Second, could it be the disk emission? What does that mean? It means that the slit-less grating records spatial info, assuming a point source that only emits 19 angstrom photons. If the telescope aims at it, the spectrum will look like this, narrow emission line. If another source is 1 arc-minute away, a spectrum will be shifted a little bit. If 1 more arc-minute, its emission line appears at a longer wavelength. On the other side, the situation is the same. So considering an extended source, you will finally see a broad emission line. The spatial information is presented in the line profiles. In the soft X-ray image of NGC 253, we do see some disk emission here. That may behave like the line winds. So are those Lyman delta lines just part of the disk emission? We checked 2 sets of the observations with nearly opposite dispersion directions. The blue boxes here and the green boxes here. Each box represents RGS observation. The blue boxes shows the same data used in Bohr's paper. I need to apologize that I haven't divided the region carefully, but you can still see the axis here for the Lyman delta line and the oxygen 8 Lyman delta line. Don't you? Here's the thing. If this is from the disk emission, it should move to the other side of the strong, like oxygen 8 line in the green spectrum here. However, the truth is this line is still at the longer wavelength side. So it should be an emission line, and this nitrogen 7 Lyman delta line has a signal to noise ratio larger than 5. It goes strong evidences for the charge change. All right, after this, we just need to explore the results. Here's the fitting with the ACX2, which contributes to the forbidden lines of the nitrogen 6, oxygen 7, right, neon 9, and magnesium 11, and also stronger, let's say, stronger Lyman delta and the Lyman gamma line of nitrogen 7 and oxygen 8. Yep, the fit results and list plot are all from the iPad notebook that you may run by yourself. So the temperature now is about 0.5 keV. Otherwise, you would be two components with 0.2 and 0.6 keV. The interface area between the hot and the cold gas is about 10 to 43 centimeter, which is one order of magnitude larger than the geometric surface area. You may use it to constrain the surface area of the cold clumps entrained by the outflow. At last, interactions velocity is about 800 kilometers per second. It's in fact determined by many different line ratios. The cold gas outflowing velocity is about 300 kilometers per second. Thus, you have got the hot gas outflowing velocity of about 1100 kilometers per second. One more thing, let's explore the distribution of the charge change and the thermal emission. We know now that the oxygen 7 forbidden line is purely from the charge change. So we generate an image of this line. But first of all, you should believe that all the observations are aligned correctly. So you can see the exposure map matches the RGS regions right. Then you see the charge change emission is prominent in the outflow region, but not around the nuclear region as marked by the black cross. The situation is similar for the oxygen 8 emission map. So where is the thermal emission? Just go to check the iron 17 lines, which are roughly from the thermal emission. You can think about why. The two iron 17 lines mixed with each other, so it's not a good idea to make an image. But in the longest observation, you can see clearly that the iron 17 line is higher than the oxygen 8. It means that the thermal emission is mainly from the nuclear region instead of the outflow region. It's quite interesting, right? In a normal soft X-ray image, you cannot tell the difference. Future X-rays, Athena and HAPS are all good at identifying the charging process. Arcs and the links with unprecedented resolution can surely do some great works on this too. So that's the bright future. Okay, let's finish the circle. Here is the benefits for the case: the temperature, the area, the velocity, and the distributions. Yeah, we will write a paper to describe all other details. Thank you for listening. That's it.
Thank you very much for keeping the time. Are there questions? I only see one here on the chat. From Junior Mao. I would expect charge exchange emission features for carbon-6 in the same model for NGC 253. How about the RGS data?
Yeah, I think we do see some higher order of carbon-6 line, but that part is not explored clearly, right? Yeah, I think there are some features, but not that evident. But
okay. Chris Down asks, can charge exchange ever be important for iron 25?
Iron 25. At this stage for the plasma around 10 to 6 Kelvin, it's not important, but for things in higher thing could be, yes. Right, this has some experts on. Okay, I haven't explored the iron 25 yet. Sorry about that.
Okay, and then Anna Ongozalek asks, how consistent is the ACX2 model and the SPECS CXC model? Are there any major differences?
That's a good question, but I said they use the same database, but they may have some different fractions. And officially, Adam is going to make some comparison with specs. So I guess Adam may help to answer this question.
Yes. Sorry. Short answer is I haven't done a detailed comparison yet. In theory, they should be very similar. But they do use, they're both based on the specs NatMDB A values. So there will be some differences in terms of the resulting spectra, just depending on what transition rates we've used. But the charge exchange data should be fairly similar, if that makes sense. But official comparison to be made soon.
Okay, thank you. We have time for one more question. Yes, there's one, Liu Gu. In specs, we are using mainly Kronos cross-sections as in ACX2, but there are a few ions in specs based on different individual calculations.
Yeah.
And that was the answer, I guess. And Steve Bromley asks, have you encountered any spectra in which the velocity dependence of charge exchange was apparent?
Yes, I said I even don't have a very confirmed charge exchange scenario for these sources, but in this one, I think it's very promising, and current state is preliminary results show the speed, but yeah, need to explore more detail into more careful region divided to see the velocity, but yeah, no real observation spectrum yet.